Hello everyone, we're going to be looking at rational functions. We're going to be working out of the notebook, so maybe let's just get started with this. Rational functions. You may recall, rational in many circumstances means fraction. So a rational function, you may see that has some sort of fraction element to it. A rational function is a function that can be written in the form f of x is equal to ax over bx, where the numerator and the denominator, ax and bx, are both rational expressions. But it's really important that we don't have bx equal to 0. So I'm just going to provide you with some graphs of some rational equations and functions here. As you probably saw from the warm-up video, they are sort of unruly at times, and it's really hard to sort of wrap your head. There seems to be no pattern in there, but I assure you there is. What I would like you to take away from the warm-up video is that we have really important lines called asymptotes. So really, the first half of this lesson is to understand what is an asymptote and what is asymptotic behavior, and where can I find the asymptotes. So please don't show anybody else who teaches math. I'm just going to perhaps define an asymptote in the following way, initially anyways. Asymptotes are critical to understanding rational functions. From a simpler perspective, an asymptote can be thought of as guiding lines upon which a function follows. From a more sophisticated perspective, asymptotes describe the behavior of a function. So it's really important to understand what an asymptote is, and let's go straight into the definition. Now, you may have to work hard at this definition to understand it, but I'm hoping to go back and maybe that we could just understand it a little bit more. The definition of a horizontal asymptote. It is the value of the function, a horizontal asymptote, the value of the function f of x approaches c as x approaches infinity, where c is a constant. Note the horizontal asymptote is a horizontal line and thus has the equation y is equal to c. From another perspective, the horizontal asymptote can be thought of the left-hand and right-hand side behavior of the graph. So really, if I was to annotate this, I am going to say, maybe take this part here. And I'm going to say, as x gets large. That's what I'm going to say. As x gets large, well, what happens? Well, what happens is this, that y gets closer to some constant c. So if I was to take a look at the three graphs, now I'm going to criticize myself on these three graphs. Unfortunately, they all have the same horizontal asymptote. But as x gets really large, here it's going negative. The y value gets closer and closer to my asymptote. And in other words, as x gets really large negative, y will get closer to 0. On the other side here, as x gets really large positive, the graph will get closer and closer, or the y value gets closer and closer to 0. Same thing on the other two graphs. As my function, as x gets large, my y value gets closer to my horizontal asymptote. So really, it describes what's going on the left-hand side, the right-hand side, on the extreme parts of the graph, if that makes any sense. So again, the function approaches, now the y value approaches a constant c. So in this case, the constant was 0 as x gets large. So let's take a look at a vertical asymptote. Now, a vertical asymptote is a little bit more interesting from a definition point of view anyways. It is the value of the function So the value of the function f of x approaches infinity or negative infinity as x approaches some c, some constant c, where c is a constant. Note vertical asymptotes are vertical lines and thus have the equation x is equal to c, where x is a constant. So x is just, c is just a constant, so allow me to revisit perhaps some of the graphs and the definitions. What we're saying here, as x gets closer to some constant. So I'm going to take a look at the middle graph here and maybe try to explain what that means. As x gets closer to some constant, the y values either get really large positive or really large negative. All we're saying. So we're taking a look at vertical asymptotes. And from the graph here, if I am seeing this correct, my vertical asymptote that I have drawn anyways is x is equal to 3. Now, here's a really bizarre part about it, is I'm going to let x approach 3 from two different ways. So for instance, I'm going to let x approach 3 from the negative side. And what I mean by that is, okay, my asymptote x is equal to 3 is that purple vertical line. If I let my function approach that asymptote from the left side, from the negative side, we see the function goes down. And it gets really, really close. The closer it gets to 3, the more negative. And one could think that as you approach it and get infinitely close to 3 on the negative side, the value of the function goes down to negative infinity. Now, here, as x approaches 3 from the negative side, alternatively, you may want to think of it as 2.99. That's as x approaches, right? Or 2.99999. 2.9999. You get the picture. Anyways, so as we approach, the graph approaches 3 from the negative side, it goes all the way down to negative infinity. Yet, on the positive side, when x approaches 3 from the positive side, so as the function approaches 3 from the positive side, the y values get infinitely large but positive. So here we would say it might be symbolized by this. By no means is this correct, but it certainly helps our thought process. So here, as x approaches negative 3, we get f of x goes towards negative infinity. But here, as x approaches positive 3, the f of x will approach positive infinity. Now, I understand you might be staring at your screen and wondering what just happened. But these are sort of fundamentally important behaviors of functions. Very, very, very bizarre. Let's continue and see where this takes us. So, just for fun, let's see if you guys can pick this up. We are going to identify the vertical and horizontal asymptotes of the following function. So take a look at this. What I would like you to do here is I would like you to factor each of these, if you can. Factor the numerator and the denominator. And when you're ready to join me, press unpause and then we can continue. Press pause. There you are. Okay, I'm hoping you're joining on me and not simply going on. The key here is to factor. Always factor. I think factors really bring out a lot of the hidden behavior of graphs and equations. So if I was to factor this, I would say f of x is equal to 4x, x squared, it's factored, x minus 2, x plus 2. Now this one is going to be 4x squared. This is g of x. And that is x minus 3, x plus 3. Now I'm relying fairly heavily on difference of squares here, right, for factoring, thankfully. I'm not beating you guys up. So now this one may be a little bit more interesting. We have h of x is equal to 4x squared Pardon me, I made a mistake there. Too busy thinking what I was going to say. So the top is a difference of squares again. And the bottom is indeed a factor. Now that's odd. I wonder what's going to happen here. But as you and I both know, we have to state our non-permissible values. So for instance, the first function f, x cannot be equal to 2 or negative 2. Over here, my function g, x must not equal to 3 or negative 3. For this one, x must not equal to 2. Now, let us look at the horizontal and vertical asymptotes. I'm just going to write VA for vertical asymptote. My vertical asymptote is, I know and you know you don't know the rule yet, but my vertical asymptote occur at x is equal to negative 2, x is equal to 2. I'm going to move on to the second one for vertical asymptotes. My vertical asymptotes for the second one are going to be x is equal to 3 or x is equal to negative 3. Now, this next one, you may be thinking, and rightfully so, that my vertical asymptote should occur where x is equal to 2. However, in this special case, that is not what's going to happen. I will try to clear this up in the definitions. So now let's consider our horizontal asymptotes. Sorry, before we go on, perhaps you are asking yourself, isn't our vertical asymptotes just come from our non-permissible values? Yeah, pretty close. Very, very close, except for in one special circumstance. We'll go over that one special circumstance, and it comes from being a common factor, both numerator and the denominator. So my horizontal asymptote here, horizontal asymptotes are much more difficult to understand. It is going to be y is equal to 0. My horizontal asymptote for the second one is going to be y is equal to 1. Very bizarre. And my horizontal asymptote here might be, oh wait a second, my horizontal asymptote does not exist. So there is no horizontal asymptote. And in fact, a horizontal asymptote is something brand new to you guys. You don't know what a horizontal asymptote, so presumably every graph that you've graphed so far has not had a vertical or a horizontal asymptote. Now, I'm just going to cross out common factors here just for fun. So h of x really is a line hiding in there. You can still cross out common factors. So h of x is our line, x plus 2. However, you have to take special consideration, as we will see, for our non-permissible values.